It looks simple, but it's not. So what we got to do first is plug in 0. Let's see what happens when we plug in 0, because that's what you would do. So we plug in 0. We have 1 over sine of 0, which is a problem. And then we have 1 over 0. That's also a problem. This problem is more obvious. This one's not that obvious, but it is. After you think of what sine of 0 is. What is sine of 0? 0! So we have 1 over 0 minus 1 over 0. Can we divide by 0 ever, ever, ever? No, no, no. So we have a problem. But luckily, the limit, taking the limit, doesn't necessarily mean we have to plug in 0 to find our answer. We can think about the way these graphs look. Okay, let's start with the easy one. This one's the easy one. 1 over x. You guys remember what that one looks like? Goes something like this, and there's like this asymptote at 0, and it goes wee, wee. It's a rational expression. You guys remember that? Okay, now think about this. We're approaching 0. So coming from the left side, as we approach 0, this graph is going down to negative infinity. Coming from the right side, as we approach 0, we're going up to positive infinity. Does that make sense? Now, in this case, positive infinity, negative infinity, they're both infinity. Okay, so we just write infinity. We have infinity for that one. This is approaching infinity when we approach 0. Okay, what about this one? Is that one as simple? Well, it depends. Do you guys remember another way to write 1 over sine? Equals. Whoa, that's a funky S. Okay. 1 over sine equals cosecant. So maybe right then you go, oh, I know how that graph looks. Do you guys remember how that graph looks? Yo, this graph is funky donkey. All right, what you do is you take this thing right here. You put the sine curve on it. Whoops. And we'll go the other way. And actually, it's supposed to be a dotted line, so you could take an eraser and like just kind of make it dotted. That's not a great dotted line. It's okay. Okay, and then every time we cross the x-axis, we have asymptotes. So the graph of this actually looks like this. You guys remember these guys? So as we approach 0, this graph is going down to negative infinity, and this part is going up to positive infinity. Kind of the same scenario as this. So we have positive infinity. Check it out, check it out, check it out. We have a positive infinity minus a positive infinity. Is this indeterminate? Yes, yes it is. Okay, now before I do my L'Hopital's rule, let's make one fraction first, because we have to have a numerator and a denominator. No two denominators here. Actually, I think what we can do is split this up, because this says minus. Ooh, I don't know. Can we split it up? I think we can split it up. Let's try it. Let's just split it up. Yeah, I think we can split it up, because you can split up the like adding addition. So we have the limit as x approaches 0 of 1 over sine x minus the limit as x approaches, actually let's keep the negative in there with it, 1 over x. Okay, so, well, it approaches 0 of 1 over x. So what we're going to do is L'Hopital's rule for each of those. What is the derivative of 1? What is the derivative of cosine? I'm sorry. What is the derivative of sine? So we get 0 over sine. Dang it! Having issues. Sorry, I'm zoning out here. Cosine x. It'll limit as x approaches 0. And then over here we have the limit as x approaches 0. Let's see, we got... Oh wait, that's 0 over 1. Are we allowed to divide a 0 by 1? Yes. Yes, we are. Are we allowed to divide a 0 by cosine? So both of these are zeros. This is 0 and this is 0. What's 0 plus 0? I mean, the limit of 0 as x approaches 0 is 0. The limit of 0 as x approaches 0 is also 0. So 0 plus 0 is 0. This is our answer. That's totally not satisfying, is it? Not at all. Alright, but that's it.